Hello everyone, welcome back to today's video. Today is the fifth day of module 1 and this is my fifth video on basic electrical engineering. In the last few videos I have discussed about the various basics of circuits, the various elements which are there in the circuit, and the different types of methods, the different types of laws uh, which are used to solve circuit. Those things are discussed. Then the main motto of start discussing all these laws and everything is to solve circuit. Use of network theorems is another method of solving DC networks. Again, network theorems are used for both AC and DC problems, but in this particular module only DC is covered because the module name is DC circuits. So only DC part is covered. In the last video I have discussed about the various theorems which are related to DC circuit. Now as told earlier, I will discuss few problems related to Norton's different types of theorems which are there. In the very beginning I'll start with superposition theorem. As discussed in the previous video, superposition theorem is used to solve DC circuits which are of linear nature. Okay, so let us begin with the first problem. The first problem is shown in the circuit. It is a circuit is shown, and it is in the given circuit below. Let battery EMF be 6 volt and 12 volt. The internal resistances be 0.5 ohm and 1 ohm. The value of other resistances are as indicated. Find the different currents flowing in the branches and voltage across 6 ohm resistor. So we need to find the current flowing in each of the branches. So every branch current has to be found out, and next is to find the voltage across 6 ohm resistor. Okay, so this is the 6 ohm resistor. So to find out the voltage across 6 ohm resistor is also asked. So after finding out the current, we can find out the voltage drop. So let's begin with the problem. As discussed, now see here in this circuit, from the previous circuit, according to superposition theorem, what we do, we remove the other voltage source or other sources and consider one voltage source or current source at a time, right? So in this problem there are two voltage sources, one of 6 volt and the other of 12 volt, having an internal resistance of 0.5 and 1 ohm respectively. So in the first step, what we do, we will remove the 12 volt battery. Okay, we will remove this. Once we remove this, since it is having an internal resistance of 1 ohm, so this internal resistance will be replacing the voltage source. Fine, since the voltage source has to be replaced by the internal resistance, or if there is no internal resistance, then the line should be directly shorted. Now see, we can easily solve this circuit. See, there are how many currents flowing? There are 3 currents flowing in 3 different branches. Here it is I1 dash, I2 dash, I dash. Okay, so let us consider this circuit. Now see, these two resistances 2 and 1 are connected in series. So it is seen that there are two parallel paths between A and B. In between A and B, there are two parallel paths, right? This and this, having resistances of 6 and 2 plus 1. Since these two are in series, the resistance here in this branch will be 3 ohm, right? 2 plus 1. So this is 2 plus 1, 3. Now this 3 ohm resistance is in parallel with the 6 ohm resistance. So the equivalent of this 6 ohm and 3 ohm will give you 2 ohm resistance. Okay. Now the equivalent 2 ohm resistance which will be coming here will be in series with this 2.5 and this 0.5 ohm. Since this voltage source is having an internal resistance of 0.5, that will also be considered as resistance, right? So this 2.5 ohm and this 0.5 ohm, that will be added up in series with the equivalent resistance which will be coming here, that is of 2 ohm value. So 2 plus 2.5 plus 0.5, so this will give the resistance of the circuit. So it is coming as 5 ohm. Okay, now we have obtained a very simple circuit where a single voltage source is there and a single resistance is there. So current I1 double dash, this current I1 dash will be given by 6 by 5. 6 is the voltage V divided by R, that is 5. Okay, so after solving this we will get 1.2 ampere, that is the current flowing in this final circuit. Okay, this current. So we have obtained I1 dash, right? Now since see this resistance and these resistances are in parallel, so if I1 current is flowing here, that current will be divided among these two branches, right? So we can easily apply current divider rule and find out the current flowing in the branches. So the current divides at any point A inversely in the ratio of the resistance of the two parallel paths, that is current divider rule. So we will obtain I1 dash, sorry I dash. I dash is equal to the total current I1 dash. Okay, that is 1.5, sorry 1.2. This 1.2 into opposite resistance. We are finding this current I dash, so opposite resistance is this total 3 divided by the total resistance, 3 plus 6, that will give you 9. So this will be 3 by 9. Okay, I dash is equal to total current, that is 1.2 into opposite resistance. This is the opposite resistance. If we are finding this current, so opposite resistance will be this. The total current is 3 divided by the sum of all the resistances is 9. So it will be 3 by 9, which will give us 0.4 ampere, that is I dash. Okay. Similarly, what happened? We'll calculate I2 dash. Now what is I2 dash? I2 dash will be equal to, similarly, the total current flowing, that is 1.2 into the opposite resistance. Now this is the current we are finding out, I2 dash. So the total current flowing here, that is I dash. So I dash is 1.2, total current that is 1.2, this resistance 6 divided by the total resistance 9. Okay, total current into the opposite resistance, that is the 6 ohm resistance, divided by the total resistance. Okay, that is 9. So it is coming as 0.8. Now this is for the first case when the 12 volt battery was removed. Now what will happen when the 6 volt battery is removed and the 12 volt battery is reconnected? So this is the circuit. See, 12 volt battery is reconnected, the 6 volt battery is removed and replaced by its internal resistance 0.5 ohm, and these are the assumed current directions which we have chosen. Again, direction depends upon you, which direction you want to take. So here it will be I2 double dash, I1 double dash and I double dash. Okay, like the previous case, we'll find the overall resistance. So 2.5 plus 0.5, 3 ohm series, these two are in series, now in parallel with 6 ohm. So 3 in parallel with 6, 3 in parallel with 6 will give you 2 ohm. Okay, 3 in parallel with 6 will give you 2 ohm. Now that 2 ohm is in series with this and this, right, this and this. So the 2 ohm resistance plus 2 4 plus 1 5, so the total resistance is 5. Okay, and now what is the current flowing? I2 double dash. I2 double dash will be equal to the voltage 12 volt divided by the total resistance. So it is 12 by total resistance, that is 5, which will give you 2.4 ampere. Okay, so we have obtained I2 double dash. Now we need to find I1 double dash and I double dash. Okay, again this line or branch and this branch, they are connected in parallel, so the current will be divided among these two branches. So we can apply current divider rule and find out the current, right? So we'll apply current divider rule. Now this I2 current will be divided. So if I am finding out I1, if I am finding out I double dash, then the total current, that is I2 double dash, the total current, that is 2.4 into the opposite resistance. So opposite is the total resistance, that is 3, right? 2.5 plus 0.53 divided by the total resistance, 3 plus 6 9. Okay, 3 plus 6 9. So I double dash is 2.4 into 3 by 9. Similarly, we will find out the current flowing here. So the current flowing here will be the total current 2.4 into the opposite resistance 6 ohm divided by the total current. Okay, so this gives us 1.6 ampere. So we have obtained for both the voltage sources, we have obtained three currents, right? Now we need to find out the overall current for each and every individual branch. So now we will consider the direction and add up the currents. Suppose, let us first find out I dash, I double dash, or the current I that is flowing through this 6 ohm. Okay, that current will be what, equal to, see the main circuit. In the main circuit, I will be equal to current flowing when this voltage source was connected, that is I dash, plus the current flowing when this voltage source was connected. Now see, this current direction is downwards, this current direction is downwards, so the overall current will be added up. See, I is equal to I dash plus I double dash, since this direction is same as this direction. Okay, so both the currents will be added up. Now let us consider for I1. Okay, let us find out I1. So I1 will be equal to I1 plus I2, right? Simple. I1 will be equal to I1 dash plus I1 double dash. Okay, so I1 dash, see the direction, I1 dash is towards right hand side. Fine, I1 dash is towards right hand side and the value is 1.2. I1 double dash is towards left hand side. That means both the directions are opposite to each other, so the value will be subtracted. So it will be I1 dash minus I1 double dash. So 1.2 minus 1.6 will give minus 1.4 ampere. Now see, the current is coming as negative. See, current can never be negative. Magnitude of current can never be negative. The negative signs means whatever direction we are choosing is opposite to what is the actual direction. Okay, so the value is 0.4. The magnitude is 0.4. Okay, next let us find out I2. Again, I2 will be the addition of I2 dash and I2 double dash. So I2 dash is towards right hand side, I2 double dash is towards left hand side. So both will be added up, but since they are in the opposite direction, so they will be subtracted. So the overall current will be I2 double dash minus I2 dash. The value is 1.6 ampere. Okay, so this is the overall current which we have obtained for each and every branch. Now we have what was the question? Find the different currents flowing in the branches. So the currents flowing in different branches have been found out, and voltage across 6 ohm resistors. Now voltage across 6 ohm resistor means what? The drop occurring across the 6 ohm resistor. So for that we need current, right? So current is I. So a drop will be what? I into R. R is 6, I is 1.2. So the voltage drop will be 6 into 1.2. So the answer is 7.2 volt. Since it is voltage, so the unit will be volt. Now always remember, whenever you solve a problem, never forget to give units, otherwise the answer will be meaningless. Okay, don't forget to mention the unit of the final answer which you have obtained for any problem. For any problem, never forget to write the unit, otherwise the answer will be incomplete. Okay, so this was the first problem, a very simple problem to just explain what is superposition theorem and how it is applied to solve circuits. Next we'll consider another circuit. On superposition theorem only we'll consider, okay? So in the next problem, by using superposition theorem, find the current in resistance R shown in figure. Now which is resistance R? This is resistance R, okay? Find the current in resistance. So this current flowing in this through this resistance and in this branch has to be found out. And what are given? R1 is given. This is R1. This is R1. R2 is given, okay? And R is taken as 1 ohm, E1 is 2.05, E2 is 2.15 volt. Internal cells are given, are negligible. Okay, see here in this problem, internal resistance of the circuit voltage sources are neglected. Okay, so next move to the problem. So firstly, let us first remove E2. Okay, let us suppose E2 is removed. Once E2 is removed, this resistance is there. Since it is not having any internal resistance, see, it is directly shorted, right? The resistance was there, see, this resistance was already there, and this line is shorted. See, directly this line is shorted since there is no internal resistance of the voltage source. Fine. So this is the circuit for the first case when the second voltage source E2 is removed from the circuit. Now see, this resistance and this resistance are connected in parallel, okay? Now notice one thing, the current direction is chosen like this. We are assuming that this E2 is sorry, yeah, current direction is given as this. So we are assuming that this E1 is giving the current, okay? So resistance of 1 and 1, equivalent of these two, since these are in parallel, we'll find out. So the resistance across AC parallel to this will be this much, okay? See, this resistance and this resistance, they are connected in parallel. So we will find out the equivalent resistance across this RAC. It will be 1 parallel to 0.04. So it will be 1 into this, and the value is 0.038 ohm. Now this resistance, whatever equivalent we are getting, suppose we are getting equivalent this, let it be this resistance, okay? So 0.038, it is in series with this, right? It will be in series with this. So this resistance is in series with 0.045. Hence the total resistance offered by the battery will be sum of this. So it will point this plus this, so it will 0.088, okay? Now again, if you want to find out the current, then it will be V by R. So it is E1, that is 2.05 by R, that is this much. So we will find out I is equal to 2.05 divided by 0.088. So it is this much of current which is flowing through the 1 ohm resistor. No. So this is the current flowing, this I1. This is the I1 current, I current flowing, okay? Now we need to find out I1. We need to find out I1 because we are asked to find out the current flowing through this. So again, this current I will be divided into 2. So the current, total current I, that is 23.3 into opposite resistance. So in these two, opposite is 0.04, right? So 23.3, 0.04 divided by total 1.04, okay, 1.0. So this is giving us as this much ampere. Now see here, now again this voltage source is removed, E1 is removed and E2 is retained. So here again, see, this resistance 0.5 and this resistance, they are connected in parallel. So the parallel, we'll find out the equivalent of 0.05 and 1. So parallel of 1 and 0.05 will give us 0.048 as the ohm resistance of equivalent of this and this. That equivalent resistance will be in series with this 0.04, right? So it is the total resistance will be 0.04 plus this 0.048, so it will be 0.088. Now we'll again find out the current flowing. This I we will find out. So this is nothing but E2 divided by the total resistance. So E2 is 2.15 divided by 1, yeah, so this much, it is 24.4 ampere. Okay, this is the current flow. Again, that current is divided among these two branches, so we need to find out this. So the total current 24.4 total current into opposite resistance, that is 0.05, divided by total, that is 1.05. Okay, this will give this much. Now notice the direction of current. See, here in the first case, when E2 was removed, the direction is towards downwards. Here also, when E1 is removed, the direction is downwards. So in both the cases, the direction of current is downwards. That means they are in the same direction. So directly the current will be added up. So it will be I1 plus I2 is equal to this plus this will give you 2.056 ampere as the overall current flowing through the resistance 1 ohm. Okay. So this is again a very simple application of superposition theorem. I hope the numerical is clear. I hope superposition theorem is clear. I hope its application in solving networks is clear. If you have any doubt, you may ask me. Okay, you may surely ask your problems. If you have any kind of doubt, you can always ask me. Okay, so these two are very simple numericals on superposition theorem. Next, I will move to Thevenin's theorem. Okay, now Thevenin's theorem, again I have discussed about it, but let me give a very brief idea about Thevenin's theorem. It says that any circuit, okay, any linear bilateral circuit that can be converted to a single voltage source in series with a resistance, okay, that circuit having a voltage source VTH in series with resistance RTH is known as a Thevenin's equivalent circuit. Okay, so now Thevenin's theorem says that any circuit, any linear bilateral network can be converted to a single voltage source in series with a resistance RTH, where this VTH or VOC is the voltage appearing across the open terminal. Okay, and RTH is the equivalent resistance of the network when viewed from the open terminal. Always remember, when viewed from the open, when we look into from the open terminals, and whatever equivalent resistance we are obtaining, that resistance will be known as the Thevenin's resistance. Okay, and the voltage appearing across the open terminal will be known as VOC or VTH. Fine. So this is Thevenin's theorem in very brief. So we'll see a few numericals on Thevenin's theorem as well. So first let us see this numerical. Convert the circuit shown below to a single voltage source in series with a single resistor. Okay, this circuit is given. We are asked to convert it to a single voltage source in with a single resistor. Now whenever this type of question is asked, you will have to understand that this is nothing but the application of Thevenin's theorem, because only by using Thevenin's theorem you can convert a circuit to a single voltage source and in series with a single resistance. Okay, so indirectly it is saying that to apply Thevenin's theorem. Okay, so this is the circuit given. Now see, there are two voltage sources present, 15 and 10 volt. Okay, okay, the open terminal is given, right? This is the open terminal. So the voltage appearing across this open terminal A and B will be VOC, or we can say, since there will no be no other voltage drop occurring here or here. So whatever voltage drop is occurring across these two terminal A and B will be same as appearing across this terminal C and D, because no further drop is there, right? So indirectly you can find out the voltage drop across C and D also. Okay, so with the terminals A and B open, the two voltage sources are connected in subtractive series because they oppose each other. Net voltage around the circuit is this. See, net voltage, this voltage source and this voltage source, they are opposite to each other. It may appear that they are in the same direction, but no, because this is open, so this is nullified, right? So they are, see, positive is connected to positive, negative is connected to negative, that means they are in opposite direction. Okay, so the overall voltage will be what, this minus this, 15 minus 10, right? 15 minus 10, it will be 5 volt. So the voltage of this circuit will be 5 volt, and if we apply KCL and KVL, will get the result. Let me tell you. Okay, wait. Uh, First, see here, it is 15 volt and 10 volt will give you 5 volt, and the resistance is 8 plus 4 because they are in series. So 8 plus 4 will give you 12. So the resistance is 12 and voltage is 5. So 5 by 12, 5 by, yeah, 12 will give you that current flowing. Current in the circuit will be 5 by 12. Okay, now drop occurring across this will be what, I, whatever is the current, into the resistance 4, 5 by 12 into 4, right? See, drop occurring across this, because this whole thing is connected in series. So whatever current is flowing here will be flowing here as well, because no current is going towards this because it is open. So no current will be flowing here, all current will flow within this loop only, right? So this 4 current 5 by 12, it is flowing through this 4. So drop here will be 4 into 5 by 12 equal to 5 by 3. Okay, after solving we will get this 5 by 3 volt. Now the voltage appearing across AB or VOC will be equal to 10 plus, see, this direction and this direction are same, right? This plus minus, these are same, so they will be added up. So the voltage will be 10 plus 5 by 3 is equal to 35 by 3. Okay, see, 10, 5 by 3, right? So it will be 35 by 3 volt. Now next step, see, this VOC is found out. This is known as the Thevenin's equivalent circuit, right? I have discussed in the previous lecture. This is the Thevenin's equivalent circuit. So here, see, this voltage source 35 by 3 volt, it is connected in series with a resistance this. So this is nothing but the VTH, which we have calculated here, VAB or VTH, and this is the internal resistance. Now how to find out the internal resistance? For finding out internal resistance, what we do, we remove all the sources. Let it be voltage source, let it be current source. We'll remove all the sources and find out the equivalent resistance as viewed from the open terminal, as viewed from this terminal. So when we view from this terminal, this resistance 4 and this resistance 8 are connected in parallel. See, RTH is equal to RAB is equal to 4 parallel to 8, because when we view from this terminal, when we view from the open terminal, this 8 and 4, they are connected in parallel. So the equivalent of 4 and 8 is 8 by 3, which is the RTH. So the overall circuit will become VTH in series with the RTH, where VTH value is 35 by 3 and RTH value is 8 by 3. Okay, so this is 8 by 3, this is 35 by 3. So this is the circuit which was asked to do. Okay, I hope it is clear. I hope the problem is clear. Now we see another application, another problem on Thevenin's theorem, then it will be more clear. Okay, now apply Thevenin's theorem to calculate the current through the 4 ohm resistor of the circuit. Where is 4 ohm? This one is 4 ohm. Okay, this one is 4 ohm. So the current flowing through this forum is asked to find out by using Thevenin's theorem. Okay, so again, Thevenin's theorem means there should be a single voltage source VTH and a single resistance RTH, right? And then for calculating the load current, since we are asked to find out the current through 4 ohm, so this 4 ohm will be considered as the load resistance. Okay, so there will be voltage source VTH in series with RTH, then the load resistance is connected. Okay, so the current flowing through the circuit will be found out. So now how to Thévenin the circuit? The first step is to remove the load. So we'll remove the load. Okay, we'll remove the load. So this is open, right? When we remove this will be open. Now we are supposed to find out the voltage drop appearing across this A and B. Now see, between B and A, when I consider like this, there is a voltage source present. Okay, so whatever voltage drop appearing across AB will not be equal to the voltage drop appearing across this. Mind it. Okay, now so the potential drop across 5 ohm resistor can be found with the help of voltage divider rule. Okay, we'll apply. So since this is open, right, so drop appearing across this plus drop appearing across this will give you the voltage drop across AB. Fine. So we'll find out first this. So this is open, so only current will be flowing here. So applying current divider voltage divider rule, it is found that the voltage appearing across this 5 ohm resistor is 5 volt. Okay. Now for finding VAB, voltage appearing across AB, we will go from point B to point A in the clockwise direction like this. So if I go like this, it will be, see, VAB means it is always B minus A. Okay, VAB is always VB minus VA. So VB, if I start with VB, it is minus 6 because it is dropping, and here it is rise, right? Here it is rise, so it will be plus. So minus of 1 volt. So the voltage appearing across A and B will be 1 volt. It means that point A is negative with respect to point E, or point B is at higher potential than point A by 1 volt. Okay. Now we have obtained the VOC or the VTH or VAB. Okay. So now next step is to find out RTH. For RTH, we remove all the sources. We remove this, and replace it by the internal resistance. If there is no resistance, it will be directly shorted, right? If there is no resistance, it will be directly shorted, and if there is resistance, it will be replaced by the resistance. Okay, so now see, this 10 and 5 are in parallel. This 10 and 5 are in parallel, so RAB will be equal to 10 by 3. So the equivalent circuit becomes equal to this much. Okay, this much only. Okay, this is the equivalent circuit VOC and 10 by 3. Now since direction was negative, since it is negative, no, so the direction, say it is minus plus. Okay, so current is flowing in this direction, in the anti-clockwise direction. So if I want to find out the current flowing through this 4 ohm, I'll apply KVL easily and find out. Okay, it will be the resistances are what, 4 and 10 by 3. So the equivalent of these two will be this plus this, because they are connected in series. So it is 10 by 3 plus 4. 10 by 3 plus 4. So I will be equal to 1 divided by the equivalent resistance 10 by 3. Okay, so the value is 0.136 ampere from E to A. Okay, so this way we use Thevenin's theorem. Whenever always keep in mind, whenever you are asked to find out current or what the voltage drop or anything using Thevenin's theorem, your first aim will be to construct the Thevenin's equivalent circuit. Your first motto should be to construct Thevenin's equivalent circuit. So for constructing Thevenin's equivalent circuit, you will require Thevenin's voltage and Thevenin's resistance. So you will need VOC and RTH, right? Or VTH and RTH. So always initially you draw this. And you then it should be in your mind to find out the value of VOC or VTH and to find out the value of RTH. Once these values are found out, directly connect the load resistance across this. Okay, then find out the current. So this is a very useful method, useful net theorem which is used for solving DC circuits. It makes the circuits very simple. See, it is a very simple circuit. It could have been solved by any other method, but the thing is, for complex problems, it will always not be convenient to apply KCL, KVL and find out. It will be very complex. So it is better to apply Thevenin's theorem for complex networks. So just to explain Thevenin's theorem, these small networks are taken, but these theorems can be applied to complex networks as well, and which will help in solving the circuits easily. Okay, so this is all for today. There are more problems to be discussed. If you have any doubt regarding Thevenin's theorem and superposition theorem or any other laws which I have discussed in the previous lectures, you can always ask me. You just give a comment and I'll answer to it. Okay, so thank you very much. In the coming lecture, I will be discussing about more numericals on Norton's and maximum power transfer theorem. Okay, so thank you for now.